Today what we're going to do is the second half of that, which is now that we know that there's complexity, now that we know how to look at systems, let's think about systems design. I'm going to cover that. Then I'm going to take a step back and put everything into context that we've learned. And at the end, we're going to do a short little mini assignment here where you guys are going to have to solve a systems problem in whatever time we have left at that point in lecture. So what makes computer systems so special? Why are they so different than a lot of other systems? Well, one of the primary reasons is that the complexity of a computer system isn't limited by physical laws. And in particular, noise doesn't limit the computer system complexity because computers are digital. And we'll actually go through a little example of what that means a little bit later on. Second is that technology changes and computer system changes at an unprecedented rate. And with this, the interesting thing is that unlike a lot of other systems like planes, trains, or automobiles, the technology we build actually helps us build better technology. That feedback loop, if you actually do a little bit of calculus, will show that the result of this is that technology should increase exponentially. The quality of the technology should increase exponentially. These two things make computer systems much more difficult in general than planes, trains, or automobiles, at least the bigger computer systems. If you think about some of the, even earlier on, Xerox copiers, you think, oh, it's a copier, what's the big deal? They're about the size of a Volkswagen. And they're incredible, and they've been around actually for more than 10 years. They have various Ethernets in them. They have something like 10 million lines of code in them. They're fabulous. They'll print stuff out at 600 dpi. This was about 10 years ago. I saw one of these operating 600 dpi, 130 sides per minute, and they'll glue bind these things. And you have this whole system there where you can use to change the. It's incredible. Right? That's a piece, even though there's a physical aspect to it, there's 10 million lines of code in it. That's a complex system. So how do we manage complexity? Well, I'm going to give you 4 different ways to think about managing complexity. I'm going to go through each of them in more detail. A couple of them you've seen. You've dealt with abstraction a lot. You probably have seen a bit of modularity. Hierarchy is one that you read about, and layers is one you may or may not have seen. As we go through these, the trick here is it's not trivial, it's not easy to just be able to say, oh, I know, I'll just use all of them, or I know when to use these. It's going to be, the hard part about this is learning when and how to most effectively use them. That's one of the reasons why you want to learn from others' experiences and what the results were so that you can have a better footing to stand on when you actually use them. So modularity. It's also known as divide and conquer. How many of you guys did the bank vault program for the interview? Okay. If you use divide and conquer, it immediately becomes a lot more easy because you don't have all these different elements to deal with. If you haven't heard the bank vault program, please ask someone who has. It's a fun little problem. The idea here is you take the components of a system and you group them together into smaller sets of interacting subsystems. Now, yesterday we talked about complexity and we talked about 5 different symptoms. Which dimension of complexity does this reduce? Modularity is supposed to reduce complexity. We talked about different symptoms for what makes a system, why it's complex. How does modularity, which dimension does this reduce?
Layers.
Pardon?
Large number of components.
Say again?
Large number of components.
Large number of components. So here what we're doing is we're reducing, in a sense, the number of components, quote-unquote components, by using modularity. We're grouping things together. Okay? And an example here is a compilation of a large program. And actually, let me write this out. Think about a large program like this one I started off talking about, 10 million lines of code. Imagine that there's there's going to be bugs in this code, and when people find a bug, you're going to have to recompile. All right? Now, the wrong thing to do is to try to recompile all 10 million lines of code. All right? But let's think about what the impact of all that is. So if you look at the total number of bugs you can write that out as the total number of bugs so this total number of bugs per lines of code is really the rate at which bugs appear in the code. So maybe you hope it's not one bug per line. You hope it's a small number. And so, I mean, this is pretty obvious, right? Because these two cancel out. Let's look at how long it's going to take to compile that. Well, the compile time is going to be the time to compile, and I'm going to abbreviate here, one line of code, right? That times the number of lines of code, right? And this is how long it takes to compile the whole thing once. But then, for each bug we find, we have to do another recompile. So that's going to be times the total number of bugs. Okay, so far so good. Great. So now let's substitute in and see what we get out. So the total compile time is going to equal this, the time to compile one line, right? And if we substitute this in here, then we say, well, lines of code, lines of code. So let's call this the bug rate. Times lines of code squared. Okay, so what's the growth rate of this what's an order notation of this compile time?
Order n squared to the lines of code.
Yeah. Order n squared on the number of lines of code. Now you have 10 million lines of code. That's getting kind of nasty. So what do people do? So if you look at modularity, modularity says let's start grouping these components, which are lines of code, into larger components. So let's say that we take let's say we group them into k components. So what does that do? Well, that just does that for us, right? Compile time now is divided by k, because if we have, for example, k files, then we only have to recompile one file. What's the order of magnitude or growth of this? Still n squared, okay? Now, the other thing that you do as programmers typically is you say, well, my files aren't going to be arbitrarily large. If I'm going to probably have, say, a couple thousand lines of code at most in a file, maybe more like maybe several hundred. So if that's a fixed size, m, so let's say m is the max number of lines of code in a file. Now this k is basically going to be m over the lines of code that we have, because we break it up into the program into components of size m. Can you guys all see that from over?
The other way around.
I can't read that.
Lines of code divided by n?
Yep. Thank you. I was getting ahead of myself. If you substitute, right, you flip this around. Yes, question.
M, I just can't read this.
Oh, I'm sorry. M is the maximum number of lines of code in a file, so it's some constant. Say you tell yourself, I'm going to do that. I'm going to put, at most 1,000 lines of code in any file, because otherwise it's too big.
So that's then the minimum k, because if they're not evenly, files are completely unknown size. The case, the total number of files is going to be significantly larger. Yeah. I mean, but you try to fill it up. Typically when you write code, you don't have a file that's like 3 lines. Usually you can probably have them average out to between like 800 and 1200 or something like that. That's the general idea here. So, but the general idea is that everything's around a constant, right? If we substitute this constant into this, right, then what do we get? Then we get the compile time
is equal to the time to compile one line times the bug rate times, and then this, because it's down here, cancels out with one of these. The m goes on top, m time lines of code. Okay, what's the order of growth of that? Somebody, what's your name? I'm trying to get everybody's name. John? John, what do you think the order of growth of this is? This one? This is n or m or n? This. Okay, order of growth of this. Why isn't it m times n? It is, but m's a constant, so it's order this. So now we've gone to from something that's n squared to more linear. So modularity, this is one of the, I mean, you can actually show mathematically that modularity, how modularity can help you. Does everybody understand this argument here?
How does it decrease the number of components, axis of complexity? Doesn't it increase that?
Well, the components here, the component was a line of code. That was each component was a line of code in this case. It wasn't a you could have defined components differently, but in this case, it's easiest to say, well, it's a line of code because the compiler, sucks in a line, parses it, right? And
but using modularity in a program doesn't decrease neither the number of lines of code nor the number of discrete components. So doesn't it increase?
It doesn't decrease the number of lines using modularity, but what it does decrease is the overall compile time.
Okay.
So this is the total amount of times. This is a simplification of the total total amount of time that you're going to need to compile this program before you ship it.
And that's what category of complexity?
The compile time?
Yeah.
It's not a category of complexity. It's a way of reducing I mean, this is an objective.
Okay.
This is an objective. You want to reduce the compile time,
okay.
and your system is this big piece of code who's made up of a bunch of components, which are these lines of code. And then so the question is, how do you meet this objective of reduced compile time using modularity to reduce the complexity of the system? And this is one way that you can do that. There's actually a critical assumption that's made here that you could use to debunk this.
I mean, you're assuming that it's if you compile a smaller part, it's like proportional to if you compile something which is 1/10 of your original, then it will only take 1/10 of the time.
Okay, that's one assumption. That's actually a pretty you're getting at the right thing. That's a reasonable assumption, but you're getting at the right issue here.
I don't know, but also you have to link them afterwards, perhaps. But I'm not sure.
Okay, you're getting warmer. You're getting warmer. I just want to get everybody's names.
I'm Joe. I'm
Joe.
just confused because if you have a bug rate and it's in, so every 10 lines is a bug in it, we'll say.
Okay.
No matter how large each of your individual files are, you're just going to have to compile that file that many times to get all the bugs out of it. So I don't see where you're saving.
You're saving because you don't have to compile all 10 million lines.
But you're compiling all 10 million lines over a period of time anyway, because you're going to have to compile each module the same, whatever the bug rate is, that many times.
Yes, but then you're getting back to when you compile something, as you put more code into it, compilers tend to do analysis that's non-local. These non-local analyses that compilers do, and this is another assumption that when a compiler does some of these non-local analyses, some of them take exponential time. And so what a compiler does actually, that's why, the compilers actually like to have smaller files, even though the optimizations aren't as great. But if you try to stuff more and more files into it, you actually have that factor that'll start coming out to bite you. And some compilers will even just say, well, I'm only going to compile one procedure at a time, because they assume that that's small enough that these exponential effects won't grab you. Sometimes if you have a huge procedure, you can throw it into some compilers and it'll just take forever, and you're like, why is this? And that's part of the reason why. But that's good. That's a good observation. Yes,
Mike.
Mike.
quick question. For the compile time, let's say you have 3 bugs in your program. It takes 3 times as long to compile as if you had just 1 bug? Is that what you're saying? For the second line.
For the second line here.
The second line, so compile time.
Well, the compile time here, this is the total compile time.
So let's say, yeah, so.
This here is the time it takes to compile the whole program once.
Yeah.
And then you multiply that by the total number of bugs.
You're assuming you only catch 1 bug per compile.
That's right. Okay, now we're getting at something that we're starting to get warmer. It's starting to get warmer. Yes.
Michael also. Actually.
Michael.
You're assuming that these systems are completely independent, and that there's no, you don't have to recompile one and recompile another.
Okay, so that's pretty close. I think you guys pretty much have it. Even though you do these modules, even though you separate these into, say, files of size 500, when you find one bug, right? Remember propagation of effect. When you fix one bug, there might be another one that pops up somewhere else, right? Or maybe there might be a lot of them that pop up somewhere else, or it might break an assumption in your code, right? I mean, there's all sorts of stuff that could happen. And if you read the Unix haters book, there's actually some interesting examples of why certain bugs have been allowed to continue in Unix. And it's this kind of propagation of effect issue. So I mean, these interactions between modules is the one thing that you could use to say, well, this argument actually isn't doesn't really hold in practice as much, because in practice you do have this propagation of effect. Nevertheless, this is a nice. I mean, this is, in general, this is the reason why you do want to break large programs into files, because you get a lot of this effect, but you still get bitten by others. Oh, let me finish up actually a little bit with modularity. When you're thinking about modularity, I mean, this is about compilation, but one of the things that people sometimes do is they try to enforce boundaries between modules to control these interactions. So in some programming languages, for example, you'll have to specify, unlike Scheme, you'll have to specify a lot about the interface of each procedure or of each module, which some programming languages have things called modules. And you'll have to say things like, here's the types of each argument, an integer. Some languages you have to specify what the side effects of each module is. Does it mutate this? Does it mutate that? Is this something that it outputs, or does it? Other languages you have to say things like what can be released and what kind of storage can be released or not. These are all kinds of ways that you can enforce boundaries between modules when you're programming. And they can be very valuable because it allows you to isolate or to try to control the interactions between 2 different modules. These things usually are done at compile time, so the compiler won't generate code if it sees an error or inconsistencies between these module boundaries. Another thing is when you're writing code or when you're doing a system, there's this robustness principle, which is assume that input can be wrong or outside of the specs or noisy, but ensure that the output is always within the specs. So one of the very first examples of this was tolerances and components. Turns out that when you used to build rifles, people used to have to fit parts together by hand. And this is because just every part came out a little bit different, and you had to maybe sand a little piece here. And so it was very time consuming, very labor consuming. What Henry Ford realized is that if you have the idea of tolerance, where you specify, here's a part, here's the measurements, and here's the allowed tolerances you can have. This then allowed the parts to be interchangeable, and all of a sudden, boom, you had that led to the advent of the production lines and cars. A really cool example is digital logic gates. Have you guys done that? Okay, so you guys have done the curve, right? Yes. Okay. All right, so maybe someone can explain it. Who said yes over here?
The idea is that a logic gate will accept a noisy value and output a clean one, so that in that transition curve it will understand from 30% higher than the voltage that's supposed to represent 0 and 30% lower than the voltage that's supposed to represent 1.
Okay.
And then when it outputs, it will output something much closer to either 0 or 1.
Right, something like this, whereas the input can be. What kind of gate is this? Flip-flop, it's a NOT gate, yeah. This is a NOT, right? 0 becomes 1, 1 becomes 0, okay? Now, remember at the first slide, I said why computer systems are so complex? What does this do that allows them to be very complex? Much more complex than most physical systems like planes, trains, or automobiles. Rob?
You don't have to compensate for noise in every component of the system.
Okay, well, you do compensate for noise, but well, the noise is reduced at every step. Is that there's going to be noise in the system? It's a physical system, but what this does is it reduces noise, and so noise is not propagated. It's reduced and taken care of at each step. So unlike imagine a car, it's physical. It doesn't. You can't. It's very hard to build components at some level that will reduce noise and however you're measuring it in another piece of it at some level. Whereas this thing just you can build these billions of transistors, put them all together, and the noise isn't going to kill you. At least not. I'll take that back if there's a designer here.
By what exactly defines modularity? I mean, all these things we're talking about, modularity, abstraction, hierarchy, they're ways of breaking down the complexity. And from what I'm gathering, it sounds like modularity is breaking it down irrespective of what is in each component.
Yeah, that's great. That's perfect segue into the next thing. That's exactly the next issue, which is abstraction. Modularity and abstraction actually tend to go hand in hand, because the question is, as was brought up, how do you decide where these module boundaries are? Usually you do that by using abstraction in conjunction with modularity. And abstraction, as you've all learned, is hiding the implementation details behind well-specified interfaces. And what you do is you choose your abstractions to try to minimize the intermodule interactions. Okay, so here again, abstraction, one of the other symptoms of complexity was lots of interactions between components. Well, now if we take modularity to reduce the number of components and use abstraction in deciding how to group these to reduce the number of interactions, we're starting to address some of the issues that complexity can bring upon us. And typically modularity and abstraction in computer science are just used it's just a no-brainer. People just do it that way. So you usually don't see the two ideas broken out apart. You may see them broken out apart in some cases with physical systems, but there's really, I can't think of a good example at this moment of why. The thing that you have to be careful with abstraction is performance. Can anyone explain why I say that?
There's lots of possible overhead in, say, if you have a piece down here that needs to pass information to a piece over here, and you've defined a nice interface path that goes up like this, but in order to get information, you have to pass it along all these and up and down all these abstraction layers when it might be much faster just to shoot it over to the component that needs it, even though that violates your nice abstraction law. Okay, that's a good general description. Let me show you this. Give you an example that. Think about this when you're reading the X window system. How many of you all have programmed in X? How many of you all know what the X window system is, just in general? Good. Okay, so you can imagine that somewhere in the X window system you have something like, create window. Right? And this function probably would take some parameters like the X and Y coordinates, whether it has a border or not, what the colors are. All sorts of stuff, right? Just because the windows are very flexible, they're very general. And so this is a great abstraction over a bunch of code that sits underneath that implements this and libraries, blah blah blah. Now imagine that you were writing a large system that did distributed spreadsheets, and so you're running around trying to figure this out. And so one of the things that you have to do as part of this is you have to say, oh, I need to build a spreadsheet. Well, what's a spreadsheet? Well, it's a window with lots of cells. Right? Well, each cell can take a number. Wait a minute, why don't I just use create window to create a bunch of these cells in here, and then I can have
it's very easy. I have all this functionality over here that I can use to put numbers in, or you color the text, or do all this stuff. This is a great use of abstraction because now you're getting all this, you're able to abstract away all these nasty details and just use create window and just do a nice little for loop, for next loop, order n squared, boom, it just comes out. Now, if any of you have done that, or some of you may be cringing at the thought of doing that, but if any of you have done that, you know that this is like the worst thing you can do. Can anyone take a stab as to why?
Well, every single one of those little windows takes up exactly the same amount of memory as one window does. So you're going to have n squared memory allocations.
That's right. So this thing is very general. So it's going to go and create all these data structures, and it's going to have all this overhead. And what do you want? Just text, maybe colored text? That's it. But why do you need these thousands and thousands of lines of code over here to do all that? You're going to take a huge performance hit. It's bad. So abstraction in this case is causing you, it's great because from a modularity point of view, you have this for next loop. But now, what's your alternative if you don't want this overhead? What do you have to do if you don't want to use this create windows function? What's that? Write your own. What's your name? Andrew. Okay. Got three out of 35 chance of getting it. Okay. Oh, right. You got to write your own. So now instead of this nice little for next loop, you have this horrible, this thing that just. I mean, you probably, since this is open source, you can go in and just grab the code and modify it, and it's this horrible thing, and now you're breaking the abstraction boundary. You're making the system more complex. This is a trade-off that's very hard to deal with, but that you have to be very careful about when you're designing your system. You can come up with a very beautiful, elegant design that minimizes the interactions between modules and just feels right, but when you implement it, boom, you get nailed. Be careful with that. If you want to read more about that, actually, I did my PhD thesis on how to actually get the best of both worlds in this. Just one approach to doing that.
I'm still having a hard time seeing how modularity reduces the number of components.
Okay. All right. Anything in?
Does it go back to that compilation argument somehow?
It's because modularity, what you're doing, if you take the number of components and you start grouping them into modules. So that's how because you start grouping them and start looking at the system as a set of modules as opposed to a set of independent components. So like in the compilation case, you're looking, instead of it as lines of code, you're looking at it as files.
Okay.
Okay.
Producing a single procedural program.
Oh, I see. Okay. Okay. Any other questions so far? All right. Hierarchy. So you all read a paper on hierarchy. On a bunch of different types of hierarchies. So you should probably know that this first part here, that the idea here is to organize your modules, in this case, into a tree-like structure. So everybody took algorithms. Everyone knows what a tree is. So each node here is going to represent a set of modules that interact. And the modules, in this case, are allowed to only interact along the links. So one example of this are businesses. If you take a giant corporation like Compaq, there's a CEO who interacts with senior management. There's each person who's in charge of a division, say in senior management, interacts with their direct reports, and so on down the line. And at some points you have teams. At some points you have just single people at the leaves. But in general, that's the structure. That structure's there. Now, like the previous example, the point here is to reduce the interactions from a potentially order n squared to order n. So can anyone tell me why that is? Why that reduction occurs? Now that you know what trees are, let's see. Someone else who, yes.
I guess because you only interact with one level up and one level down, while in abstraction theory you can interact with anything.
Okay, so in a tree, good. All right, if each of these has modules, and then basically you only interact this way, and within this module here, right? And because of the nature of the tree, you know that most of the tree isn't going to be if you distribute it, assuming you distribute it well, in a more or less balanced way, most of the tree isn't going to be in here. And the size of this is going to be, of each one of these nodes, the number of modules in there is something that you're going to want to limit probably by a constant, because if you put too many modules in there, then you're faced back with the same complexity problems. All right, does that intuitively make sense? Any questions on that?
Yeah, why don't you have the daughters of a node interact among themselves rather than create a node with dots inside it?
Why don't you have these are modules in here.
Simon's example of a room reaching stability of temperature,
Mm-hmm.
the cubicles interacted among themselves.
Mm-hmm.
Ultimately, a room
Mm-hmm.
aggregate interacted with another room.
Mm-hmm.
So why aren't there inter-sister connections?
Well, in this case, you mean like this?
Yeah.
Well, in an organization like a business organization, at time you don't necessarily want this because there's no reason to do it. So assume that this one, for example, is a division that does. Suppose the way you divide this is geographically. So this one's it's a sales organization in Mexico, and this one is a sales organization in let's pick Japan. Right? For these two to interact directly doesn't make a lot of sense. Up here, where there's, let's say there's another sales thing. Up here, who's the director of sales, say of notebooks. There it makes sense to see, well, what's working here, and kind of look at it all, decide what, and then kind of propagate back down. But for these two to interact, doesn't really make a lot of sense. So that therefore you can organize the hierarchy this way. Now, the other side of let me extrapolate to the other side of that question. There are lots of different types of hierarchies. There are lots of different ways of using hierarchies, and you've read about them in this book. And as I mentioned before, it's not always clear which one is the right way. So one of the things you have to decide when you're looking at a system and you want to use hierarchy on it is, how do I want to organize the hierarchy? How am I going to, how can I actually do it? Am I going to have weak interactions here? Maybe you might. If you might, then it is what it is. Yeah, it is what it is. And when you design systems, it actually, if you look at organizations, you will see weak interactions between these at times. And that's fine, but having this as the overall guiding principle will help reduce a lot of the complexity. Other questions?
So you consider hierarchy a special case of modularity?
Well, I consider hierarchy a way of organizing your modules.
So you wouldn't have hierarchy without modules in a computer system?
You wouldn't have hierarchy?
You wouldn't have hierarchy without modules in a computer system?
You could. You could make these components. I'm just assuming that if you have components, you probably want to organize them into modules to begin with. In the modules, you'll decide based on the purpose that you're looking at, based on the objectives, that kind of thing. But I'm going to be talking in terms of module. I'm talking in terms of modules here because I'm assuming that you'll always want to take that step.
What's the distinction between modules and components?
A component can be, for example, like we were talking about yesterday, a component can be, in the case of a computer, let's say, can be the disk drive, the cables that connect the disk drive to the PCI, to your PCI SCSI card, and the PCI SCSI card that connects to the right. You can modularize that into, say, this is, and use abstraction to say this is a disk subsystem. But your system could still be all these different pieces, right? Because you might be thinking about, well, my objective is to make the whole thing go fast. Well, then you have to think about how wide my bus is at some level. So you still want to think about those components in your system. But when you're thinking about the other side of that disk subsystem, like the interface between the PCI card and your motherboard, then maybe you want to abstract this away as a module.
So in a programming example, what would modules versus components be?
A component could be a set of procedures, and a module could be an interface to, say, creating and modifying windows.
I don't see that difference yet. It sounds like module is just a higher order construct. You're talking about modules as made up of components.
That's right. A module is a higher order construct that helps you reduce the complexity of a system when you're looking.
That's the distinction you're making between component and module?
That's right.
Okay.
That's it. Mm-hmm. Other questions?
Is it fair to think of component as your sort of lowest level of
Yes.
analysis?
The lowest level of the system that's relevant to what your purpose or objective is in analyzing or designing it. A lot of times when you're looking at your system, you'll actually want to look at it different ways at different times, depending on whether you're optimizing certain things or designing other pieces, etc. So layers is an interesting technique. Uses modularity and abstraction, and it's just about looking at a system a different way. So as an example, and layers doesn't necessarily add more functionality to the system. It's just a different way of looking at it. So one way of looking at this computer is, well, it's a bunch of logic gates and memory cells. At some level, that makes a lot of sense, because you might be, working at that. You might be thinking about, what kinds of, how much power do I have here, and what is my cache line size, and a bunch of different parameters. At some other level, you might say, oh, it's a microprocessor, and it's got these little subsystems in it, or modules. There's the cache here, the level 1 cache here, the level 2 cache here. There's the floating processor unit, and so on. At another level, you think, oh, it's a machine language processor. I can feed it machine language instructions, load register A with the number 1, do a comparison and branch if necessary. Another level, you can think of it as a Java processor. Well, I put in these Java bytecodes and it computes some answer. This is all the same machine. You're just looking at different layers of implementation. Okay? Yes? Question? Okay.
I was just thinking, presumably at a still high level, you could think of it as a word processor.
At a higher level, you could think of it as a word processor. And if the word processor is something like LaTeX, then you're still at the same point, because LaTeX is actually Turing complete, so you can actually write any program that you want. Do you guys do complexity yet? Okay, so you know what Turing complete is. Okay. So what else? Well, I've given you these different concepts to play with. It's going to take a little while to really understand them. It's going to take you actually working with them to get an intuitive feel if you don't have one already. And the real question, the thing that you have to learn is, how do you pick the right form of modularity, abstraction, hierarchy, or layers? If you looked at the architecture of complexity paper, as we talked about before, there's lots of different hierarchies. There's different ways of organizing them. There's different effects that you get out of that. There's no right one, but this just illustrates the point. If you're given a priori some system and said, turn this into a hierarchy, you have to decide how to do that. But there is some help that you can, in terms of deciding that. There's a couple of different approaches that you can use to try to help you decide what form of modularity, etc., to use. One is called iteration. Second one is called KIS. I took the last S out. So iteration. The idea here is you start with a really simple working system that meets a few of the key requirements. Does this sound familiar? Worse is better. It's very much aligned to that type of philosophy. What you do is you use what you learn. You study the system, you use what you learn, and then you evolve it out to start meeting more of the requirements. Now, one of the things that's key here is that you need to make sure that you study all the failures, that you learn from your mistakes. You really work the system, figure out what works, what doesn't, what could be done better, use that to help you along. One other advantage of this is that you can import new technology as it arrives. So as you know, technology changes so fast, something new comes up, suck it right in. Trade-offs. Well, one of them is what I call the kitchen sink syndrome. And what that means is, if you're using this, it's likely that you'll say, oh, well, now that I've done this, let me add some more features. Oh, and now I can add more features, and it keeps evolving, and you never finish. This is something very dangerous, especially if you're going to go back into the software industry, and you're going to become a software engineer. Your manager is going to try to make you add as many features as possible, and they're going to keep adding things. So be careful when you're using this approach. When you use this approach, you always need someone, whether it be you or someone else, to make sure that the original design goals and conception of the system are being kept and are being abided to, because otherwise it'll just get out of control. Second thing here is that it becomes harder to change your early decisions as time goes on. So a decision that you made very early on after you start evolving and iterating, it's very hard to go back and change one of these early decisions because of propagation of effect. Right? Changing something early tends to have a greater impact on the system than changing some decision you made later on. Okay. Next one is keep it simple. And I found a couple of these quotes. They're real. I love them. If in doubt, leave it out. I mean, if you don't know if this feature is going to be useful, or you don't, it's cool, but you're not quite sure, out. According to this approach, Albert Einstein loved simplicity, but not too much of it. I would guess he was alluding to, don't make, you can take Newtonian relativity and reduce it. If you keep reducing it, making it more simple, it might become Newtonian mechanics at some level. So what problems do you face here? Well, it's kind of hard to convince people that you want to leave stuff out. So imagine that you're building some system. Your manager is going to say, well, we need more features. Why? Because if we put this out, even though it's simple, our competitors are going to have more features and we're going to lose. So what's a company out there that loves throwing features into things? Yeah, loves throwing features into things. And why? Because they think, that the more features you have, the better. Upgrades. Why upgrade to this versus WordPerfect? I mean, there's all sorts of marketing around that. Another thing, there's a lot of things you have to be careful, but they're all of this type of flavor. Imagine that your manager says, well, everyone's already tested these features independently on its own. Why do we need to keep it simple? Let's just stick them all together and go with it. What's the problem there? Yeah, well, emergent effects. All right, you put them all together, and this is, never believe anyone who says like, oh, we've tested them all independently and we put it together and it's just going to work. Right? Because you don't know what these emergent effects are going to be. Okay, so let's step back a little bit and think about what we've talked about the last couple days and put it all into perspective. So we talked about analyzing systems, right? How do we look at systems? How do we think about systems? And the big question is, what are we dealing with? When you're given a system, how do you add structure to what you're given? And we looked at what a system is. There's components, there's an interface, there's an environment. Below that, you have to think about what the purpose and granularity is. If you know that, then at least you have an idea of the system you're talking about. But what about, but you have to think about it on a broader scale. So let's think about, for each system, you should also know, what problem is it trying to solve? What approach is being used to solve that problem? I mean, each system is there to solve a problem. There's an approach that was used. There's probably the system itself is, in essence, an experiment. What are the results? How can you look at that system and measure it to see, what metrics can you find to see if that system has met its objectives? What conclusions can you draw, and what would your next steps be? We also looked at a complementary framework in what I sent out last night, which is, before you respond to anything, you should know what assumptions are being made here. What are the objectives of this thing? What are the trade-offs that are being made? And we also looked through a set of objectives. There were something like 8, and yesterday there were speed, robustness, availability, fault tolerance, etc. If you use this framework here, if you understand the system, you'll be in a really good place to start debating real issues and not going into some kind of Wild West type thing where, right? And these are the kinds of things that you should try to get up front before you respond. We also looked at, in terms of analyzing systems, where do we look for issues? When someone says, what do you think about the scalability of this system? Look at, there's at least three different places you can look for that: the emergent effects, propagation of effects, and commensurate scaling. So this is a framework that you guys should use ongoing, not only for your own reading, but also remember later when you're discussing in recitation section, think about things this way. This will help you focus. So on the one side, you have some more of analysis and critical thinking. On this side, you have more of design issues. And when you're starting to do your final project, these are the kinds of issues that you should think about when you're considering what you're going to design and what people are going to ask you about it. Questions so far? Okay. So let's go back to this. Can airplanes really fly? Now that we've looked at all this, let's have somebody explain why, take a crack at why this is not true. Yes?
We're leaving out thrust.
Thrust, okay. So what about thrust?
In a small kite to get enough lift to fly.
Okay. Now that's an interesting point. Unfortunately, at this point, when people were arguing this, there was no such thing as a jet engine, and this whole like putting a propeller thing was pretty new too. Are there any other arguments that you could make besides thrust that could support this? I mean, because back then, you saw these funny flying machines that people would build, right? They would look at birds, with birds flap their wings. They thought, well, that's how it works. Yes.
Two things. They're not taking into account different designs, different. Obviously, an airplane isn't a bird. It doesn't act like a bird. It doesn't do anything like birds. That doesn't operate based on the way a bird operates. And the other thing is, it says larger flying machines, but it doesn't say how much larger. Maybe if you made a kite out of exactly the same materials that was the size of the World Trade Center, it wouldn't fly. So
well, this is getting interesting. Kites. Okay, it's Sham.
The first assumption that weight grows with the cube of the size can be overcome.
Okay, and how do you
change the density? So
change the density? Okay, we're getting.
The fact that it says it grows as a cube of size implies that we're assuming that it's solid and that it's filled.
Okay, good. So now we're actually getting to something nice and crisp. So let's put all three of these things together. Kites, structure. Kites have been around for quite a while, right? Is there a way that you could use kites to prove this wrong? Anyone fly kites? Kites are great, right? You throw them up and.
You really can kind of make a kind
yes?
of
Things like hang gliders are kind of very similar design, I guess, as far as materials go.
The interesting thing about hang gliders is you can't. Hang gliders, you depend on air currents, right, to propel yourself. Whereas you throw a kite up and it just it pulls you. There's actually real energy pulling you up from that without. It's because of the wind.
Hang gliders will work that way too.
Okay, hang gliders will work that way too. But if you had a kite, they didn't have ultralight materials back then, right? They had wood and metal, right? So, in theory, yes. But a kite is something that they had back there. Go with me here.
It's like
kite.
It's like the effects of wind is the dominant effect on a kite, not gravity. Whereas a plane, gravity is more dominant than wind.
Okay, so wind is used. The kites use the wind for thrust.
Dropping a feather versus dropping a brick.
Okay, so how can you use this idea? There's wind that's providing the thrust. There's kite. There's this notion over here that volume and mass aren't necessarily related. So think about, you're flying how can you show this just by using kites?
Well, a kite is a kind of attempt to be as close as possible to a series of planes rather than some kind of cubic object.
Okay.
To maximize.
Tubular kites. They're tubular kites that don't have a large surface area relative to the volume.
Okay. This is starting to sound. So what kind of kites? Yes.
Well, it's also, the pull of the kite is much greater than the weight of the kite. That's why it's pulling you up. So obviously it can support much more weight than itself. That's why it pulls you when you're pulling it.
Okay, so let's think about that. So if we put two kites together, right? Well, how much pull are we adding? Roughly double. And how much weight are we adding? Double? Are you sure? Why double? Because they're okay, so you have double. Pardon?
The weight of some connecting material. Well, if one kite can fly, then the ratio of
pull to weight is in favor of pull, so doubling it is going to double the favor. I mean,
also the mass is double with the weight you're saying.
Okay, now start thinking about, that's right. So now start thinking about like this is actually what someone did is they thought about box kites, right? And you have these box kites, and imagine you start connecting these box kites up. And what do you need to connect them? Well, almost you don't need very much. And you know that these things can support a lot of weight. So if you start connecting a bunch of them together, right, then this myth here is debunked, right? Because you can scale that up in a way that doesn't require the scaling of that allows you to grow the tug, the pull, without and it allows you actually to add more weight along the way too. So this is the kind of this is the kind of thinking like this that it's not trivial, right? But it took a lot of smart people believe this. But this is the kind of there's usually this little aha or like a little experiment that you do or that actually gets you over the hump.
Aren't you assuming that the wind interacts with something 12 times as large the same way it does something that's just 1 unit?
If you add a bunch of these kites together, though, right? I mean, there's.
But you're assuming the wind still interact that the wind.
Yes. No. You're right. You're right. Yeah. That's right. But the point is that people did this experiment, right? They put a couple kites up. They put more kites up, and they showed that you could have more and more mass flying up there, and from there you can say, well, maybe we should actually start thinking about this, not believing this, and start thinking about ways we can design gliders or planes or something that will actually fly. I mean, the problem with this argument here is from what I read, I mean, this thing stifled aeronautics for a while, this type of argument, and unstifling it and letting creativity come out was what was needed, and a simple experiment is all you needed to get over that. But now let's do something a bit more complicated. So, and let's use what we've learned so far, and this is going to be a class participation effort. Joe Schmo comes over and says, Joe Airline comes over and says, I want you to help me. I just bought, a bunch of planes and a bunch of space at different airports around the country, and I want you to help me design my traffic grid. And he says, okay, if I look out there, there's basically two types of grids. There's the hub and spoke system, and there's what I'm calling multi-stop traffic. So let me describe to you what those are. Hub and spoke. Does anyone actually know what that system is? Rob.
It's like the Delta system where most of the flights go in and out of
Atlanta or Chicago for United. Good. Houston Continental. All right. What about this other one, the multi-stop? I couldn't figure out the best name for it, but there's another airline in particular that uses a very different system. Southwest. Okay, tell me what they do.
If you want to fly from New York to Los Angeles, you have to fly through every city in between.
Okay, great. Now, can someone tell me which airline the head of the CEO of American Airlines hates the most? Southwest. Why do they hate Southwest?
They have lower prices.
Yeah, they have lower prices. All right. Okay. Why do they have lower prices? We don't know. I don't know. I mean, I don't know. There's actually a lot of business reasons, but
one reason might be that although it's certainly less efficient for the traveler to do that, bouncing down the country from the perspective of fuel and expense to operate the aircraft, it might be much more efficient. So.
Yeah, I mean, you can probably imagine there's different things like, we'll go into some of that. So that's the background, right? There's both of these things exist. They're both commercial. They're both around. What are objectives? Well, what you have to decide is you have to be able to get market share. You have to show how you can get market share, and you have to show how you can lower the costs. Those are the two key objectives. There's a lot of other ones, but those two have to be optimized. Here's a set of assumptions that Joe Airlines is going to give you. There's a fixed delay between an airplane landing and taking off, just as a simplifying assumption. The average flight is 2 hours long, given the layout is traffic grid. So what I want, so in the next, say, 15 minutes, let's start working this thing out. And at the end of all this, we're certainly not going to get done to where we could give an answer that would be the best answer. But I want to take you through this, and I want you guys to figure out, and I want one of you guys at the end to tell me which one you would recommend and why, based on what we figured out here. So let's start off with the assumptions. Are these all the assumptions you need to come to a reasonable recommendation, or are there others? Oh, good. Okay, hold on. Assumptions. Don't forget what the objectives are here. Okay, raise your hands if you've yes.
That there's enough runways and air traffic controllers to do all the flights you want to do.
Okay, let's write all these down. Runways. What's that? Air traffic controllers.
Something about there are not enough runways and air traffic controllers in place to handle all the flights that are scheduled on any given day.
Okay, so you need enough. And that's a concern, but what do you need to, what kind of assumption? Are you making the assumption that there are enough? Is that what we should do?
You need to know what the limits are.
Okay. All right, so need to understand. Okay, let's write about 6 or 7 down, Sharon.
You need to make some assumptions about planes breaking down and where you're going to have parts, especially if you're doing a
okay. So plane maintenance, parts, labor, center. Okay. Who else? Yes.
Yeah. Are we carrying passengers only? Can we carry cargo at night?
Okay. Passengers versus cargo. Yes. Oh, that was, the same one. Who else? Yes.
How many planes have we got, and how much capital? And I think you can put it, make the first one a little bit more focused by saying there's landing slots at a city that you're going to service. The first one, runways and ATC, I think it's really a question of landing slots in a city you're going to service.
Okay, so landing slots. And then this is how much money you have, right? Okay. Yeah.
Get pilots and stewardesses.
Okay, how many pilots and stewardesses? Pilots and flight attendants, right? All right, others, yes.
You need to know something about the demographic, whether they're going to be willing to pay $50 less and have 4 hours more air travel.
Demographics, dollars versus time. Okay, yes.
We probably need to know what kind, in line with demographics, what population you're servicing. If you're just servicing people within states, that are doing local travel, that's going to make a big difference.
Okay, type of travel.
National
travel, local versus non-local. Let's take 2 more. Yes.
Seasonal and special event variation demand.
1 more. Yes.
This is kind of like plane maintenance, but it's, is it more wear and tear on a plane to land and take off than just fly? Because then you're going to need to repair, you're going to be spending more time repairing planes than got to land in all of the cities.
Okay, wear and tear on planes.
We also have to consider the cost of loading and unloading.
Snuck it in, huh? Cost of loading, unloading. Okay, so we have about 10 minutes left. Do you think that, let's look at this list. What's wrong with this list? What's that?
Well, for 10 minutes is great many points.
This is way too many. This is way too complicated. I mean, look at this thing. Let's pick what are the top ones here that would help you come up with some answer.
Number of planes.
Okay, number of planes is important.
What people like is pretty important if you're going for hard code.
You can condense all the demographics up into sort of what type of service you're offering. I'm kind of generalize that.
Okay, so we can turn some of the demographics, some of these things into the into service, type of service. Yeah, so this is what I think. This is what that's like. That's saying is what type of service. So you know how local versus non-local, that type of thing. What else? Pick one more. What's the if these two are, pick a third one. Say.
Budget constraints.
Pardon?
You have how much dollars, how much capital you have.
How much money you have? Is that? Do you think that's the maintenance? General facilities. Well, let's look back at this. Market share and low cost, right? We've got market share. Which ones of these? So type of service is going to help us a bit with market share, right? And how are we going to do anything about the low cost? What's that? What do we need? What's an interesting thing to know here?
Overhead per flight, essentially the cost of landing, the cost of loading, unloading, the wear and tear.
Okay.
Cost per flight, the number of flights.
Good. Cost per flight. I think that's so the cost associated with flights. Okay, good. So these kinds, if we knew these kinds of things, I think they would go towards helping us. Is there any kind of analysis that we can do to compare these two types of the hub and spoke and multi-stop without even knowing these things?
How many flights someone would have to take to get to their destination? I mean, I'm not familiar with multi-stop from the sounds of it. What everyone was saying, that most people take more flights to get to their destination than multi-stop.
Okay. Well, let's look at.
More than anything else, we need to know about demand for who is where and who wants to go where.
Yeah. Well, let's look at the structural differences between these two, hub and spoke and multi-stop. And one of the things that was, let's look at, without even knowing what they are, let's take these as sort of as variables. Cost associated with flights. Okay. What's the cost associated with a flight? Let's look at the hub and spoke system. Let's assume that we have one hub. So what generally happens? Let's think about how this system works. What generally happens when in the hub and spoke system? You guys who have flown. Okay. So but what about the timing between these flights?
Usually they're late anyway, so it doesn't matter.
That's right. That's right. Actually, that's a huge disaster for these guys, right? For that hub and spoke. But what happens? These guys all fly in like at the same time, roughly, right? They're all timed to fly in at the same time. Everyone kind of switches, and boom, everyone flies out.
So how many
right?
flights can you get in and out every day?
Yeah, how many flights can you get in and out every day? There's some considerations, like for example, the ATCs and runways and all that. But assume that the reason this guy bought these things, right, was because he was smart enough to know that he had enough runways and ATCs, because otherwise you wouldn't buy a plane and the rights to a certain flight. But let's just look at the structural. So everyone kind of flies in, everyone kind of runs around, everyone flies out, right? So how much, in terms of what's the cost of people flying in? Well, there's the plane landing and landing fees and all that stuff. What's another? So there's landing, airport fees.
Isn't the cost of taking off the fuel cost a significant portion of the fuel cost for?
Depends on the length of the flight, right? If it's a short flight, but let's just look at what happens when everyone flies in. You pay airport fees. What else do you pay? What's a big piece of what you pay?
Fuel.
Well, fuel, but planes, take off, land. You have to pay the fuel. What's that?
To service the plane when it lands.
Okay, so service the plane. What else? And that involves what?
Cleaning the plane after.
That involves people, right? Okay, so you have a huge people cost. Sorry, I'm using a different color.
Although the people cost is probably less with the hub and spoke because you've got economy.
Well, let's think about that. People cost. So let's just draw a quick graph. what's the number of people? So what's the how do you determine how many people you're going to need there?
You need X number per plane, and you need, since all the planes are coming in together, you need, it just goes linearly out.
Okay, so you need enough people to handle the maximum number of people that are coming in at once.
Yeah, because all the flights are in at the same time. So if you need X per plane, if you need 4 people per plane, you need 4 times number of planes.
But you can
schedule yeah, so I mean, in this system, what happens, I mean, the assumption here that we're making, a simplifying assumption, everybody flies in, right? Everyone switches, has an hour to switch around, then everyone flies out, right? Then the cycle repeats at some point. Those flights drop people off, then they pick more people up, and then they fly back in, they drop people, and then they fly back out. This is just like a one. So what is the required utilization look like of people?
So you have a peak, and
then
nothing happens, and then it peaks like that.
Right? This is when the people come in, right? This is peak when everybody's there, and right? And what kind of and when you staff this, how many people do you need to staff this with? You have to staff to peak.
Do part-time workers. Come in for 3 hours.
Yeah. Okay.
Could you try for an out-of-phase curve?
Pardon?
Could you try for an out-of-phase curve to fill in the value?
There's lots of tricks you could try, but I mean, but they also cost money, and you have to figure. It makes things a lot more complicated, and there's a bunch of tricks that I won't claim I know, but I know they play a lot of tricks to try to. But I mean, this is Joe Airline, right? This is a new guy. He's got some planes. This is what he's faced with hub and spoke. What about the multi-stop? For what's the number of people that you're going to need at each stop? I mean, maybe you have like a couple coming in, a couple going out.
Just one fly.
Okay, and these things are coming in, like who was saying that they were just, you fly everywhere in between, or you can stage these, right? If you're flying from LA to Seattle, right? You send one. It's very easy to stage these at a finer granularity than it is to do the hub and spoke thing, because the hub and spoke thing, right? You may have someone coming from way over here and someone coming from over here, but yet everyone has to show up at a time when they can, run around and go to the next outgoing flight. Whereas over here, you can stage it at whatever granularity is best for that. So does the utilization curve look like this?
More constant.
It's probably more flat, right? And it's probably lower, right? At each particular place. Overall, because here you have a hub, so it's right. And here again, you have to staff to peak. Right. So what does this tell about our labor costs in the two different systems, in the two different ones? Right. Where's the waste? All right. Question. Times the number. And this times the number of hubs. This times the number of stops.
Seems to me as though it's one of the advantages of the hub and spoke, though, wouldn't be in operating costs at all. It would be in setup and infrastructure, which must be an enormous part of the business. The fact is, if you are one of these big airlines and you create a hub, you don't have to deal with the business of constant negotiations of landing fees at somebody else's airport. I don't know whether these guys own the airport themselves, the hub, or whether they're just the prime leaser, but there must be economies of scale in the infrastructure and setup.
Yep, that's right. So that's right. Question.
Are we assuming that the kind of stop along the way has sort of more stops that are more important than others? Because if they don't, then you sort of have to replicate a maintenance infrastructure for critical maintenance.
That's right.
Multiple times.
Right. There's a lot. Yeah, go ahead.
Well, it just seems to me that if you took the smaller wave and then you multiplied it by, stopping at 10 cities along the way, you're still going to wind up with the same amount of waste, except distributed over a greater area.
Is it?
I don't know.
Is that? I don't know.
I mean, if you have, if you have 10 stops to go from one city to another.
The reason I wouldn't make that assertion is because I would argue that may or may not be true. And it might not be true if these stops or places are smaller airports that, in areas, different types. I mean, here you're talking about Houston, big cities, right? San Francisco, Chicago. The differences in labor pool here versus here might offset something like that. Yeah.
You're still hopping. Flight patterns are still going to land in big cities at terminating points.
Mm-hmm.
So you're going to have order of magnitude sized labor costs like the hub system at some point in the flight.
Well, I mean, if you're landing one every so often, why wouldn't it look like this if you're in a major city? You're pumping these guys out to Seattle, say, right? And you're not pumping in a whole bunch of them from everywhere. You're doing this,
Right. Well, you just said you're talking big cities like Houston.
Oh, we're talking about the hub and spoke.
Big labor costs. The hopping system is going to still incur big labor costs like that at big cities, the same as.
Yes, but because you have to staff at this level versus this one, then you can save on that. I mean, let me step back a little bit before. Now, this isn't a proof that one system is better than the other. Okay, the point here is to show that. I mean, here's one way to jump into it is to go boom and start right. But if in the real world, you're not going to have all the time that you need to look at every single possibility and think about every single thing. You're going to have to very quickly start thinking, well, what are the critical aspects of this system that I need to look at and use those as a way to try to focus my design. Now, this is an example in a way of iterative design because here we have one way of characterizing this system. We have it's a simplified one that meets some of these objectives, right? Market share versus low cost. Cost here, market share because we can pump people out, lots of people all over the place along the way, and it makes a lot of sense at this level. There's a lot of different roads you can go down. There's a lot of different things you'll probably want to know, which relate to this. Some of which someone may have done an analysis on, some of which they may have not. But the point is here, be careful about jumping into something like this. If you feel yourself when you're coming up with an answer to one of the questions that I give you, when someone asks you to analyze a system, try try this approach first. Take one aspect of it, something that you can actually you can analyze, you can push forward if you want to. That's an important aspect that actually addresses the objectives. Start there. And then see where that takes you. What that'll help you do is prune this. Like maybe if you push this forward, some of these here matter more than others, and that allows you to narrow down what you actually need to know, what you don't need to know. Try to structure the way that you approach these things that way. Try to start off at the high level. Does that make sense? That point get across? Now this is a fun problem because I mean there's people who think about these airlines have people who think about these kinds of things and who constantly, I mean we're talking about the phase shifting and do all sorts of things to try to make these schedules so that to minimize these down here. But what's true out there is that there's an airline that uses this that's very successful. There are airlines that use this that have been somewhat in turmoil. Some of them have gone out of business. Some of them have merged to try to improve their economies of scale. But they're two systems that work that have different objectives that meet different criteria. So again, there's no wrong or right. But when someone asks you to design it, you have to think about what you can learn from these two to come up with your recommendation. So can someone come up with a recommendation, either one of these, and choosing either this model, the hub and spoke, or the multi-stop, and tell me why they think that's the right one, based on the very little information that we have here.
This amount of simplifying assumptions.
You have to be, yes, a brave soul.
Going solely based on the experiences that we can see currently in the airline industry. If our objective is low cost, we would want to follow the model Southwest does. We don't fly out of Logan and JFK. Instead, we fly out of Providence and MacArthur and these smaller fields that have lower cost, that have lower maintenance costs, lower airport fees. And we follow that model because history has shown which of those models, currently anyway, is more successful. So we base our potential success on the success of things we've seen beforehand.
Okay. What do people think about that? Yes.
Well, it seems like basing what we want to do exactly on what is sort of out there in the market and what people are doing might be sort of exactly the wrong approach, right? Because if it's, you know, it may be sort of, I mean, obviously, like, you know, United and Delta and airlines like that are starting to kind of tumble based on this model. But, you know, if like 5 years down the road, you know, those large airlines have all failed, and sort of every airline is out there in the market, you know, they may be able to offer much cheaper fares doing this sort of, you know, jumping around system. But then that market of people who are willing to pay a little bit more for the convenience of not stopping, you know, in their flights, it might be a more sort of elite market. But if no one's meeting that, it might be a much better business model to go there.
Okay, now you have to be careful with that type of argument. The type of argument that was given over here was one based on history. Like history, you know, has shown this to be true. And of course, we all know that past performance is no guarantee of future results. But the argument you gave was very speculative. So you gave, you know, what if this and what if that and what if this. So you have to be very careful about that because, I mean, as we saw yesterday, what ifs are easy to knock down and easy to disbelieve. So if you give a what if, you have to back it up with why you think that's more likely. Yes?
You could try and make it a bit more specific by speculating that perhaps the multi-stop approach, one of the reasons it might work for Southwest is because not that many people are doing it. Yeah. But if there were wide-scale adoption of that, there'll be more takeoffs and more landings, therefore the average landing fees, the things that Michael was talking about, using low-cost airports, low-cost landings and so on, the industry average would be driven up and there'd be more people, more competition within that model. Maybe one of the reasons it succeeds now is because there's not that much competition within that model.
Mm-hmm. Yeah, and so that's, I mean, but the thing is that doesn't necessarily debunk what he said. It's another, you know, you're speculating again. We don't know for a fact that if there were more airlines that these costs would increase. Maybe it would improve the economics of scale at these small airports. It's unclear. The thing that you know, he made a statement which he said, basically saying I'm going to bet on past performance as a somewhat of a guarantee of future results. Now, the thing that you should come back with when he says that is to ask him, well, can you outline the 3 key risks that I'm going to face by doing that? Because whatever approach you use, there's going to be risks. This gets back to the trade-offs, right? If you say if you make a recommendation or you make a point about something, you should understand what the other side is. So why don't we ask him, what are the 3 key risks of doing that, going through that approach?
I'm assuming that the large airlines stay with hub and spoke. If everybody decides to switch to this, then their economics of scale are going to squish it.
Okay. Do people think that's a big risk? What do you think?
Well, I just think it's difficult because this is not based on the analysis that we've done. We're basing on other factors, and there's a lot of questions in my mind. You know, how long has Southwest been making these profits? And I think it's difficult to make a really good decision.
It's always difficult to make a really good decision. That's the whole point about systems, is that it's always difficult. And so the problem that you have to do here is you have to step up to the plate and say, I'm putting my flag in the sand here, and I'm never going to know what the right answer is because by the time I do, it's already been done. You know, it's too late. And I mean, if someone can tell you, if someone walks into your office and says, I'll build your, you know, you're doing a startup, I'll build your system, and I guarantee you this is the right decision. I mean, you'll never believe them.
Market shares, I would want to take a look at their market shares. I mean,
we just and their customer manage about
there's a whole set of things that you'll have to look at. If you're in the real world, you may have a week, you may have a month. I mean, I've been on studies at McKinsey where they say in 1 week you have to cut 20% of the workforce of an 80,000 person company. 1 week, right? I mean, this stuff, it isn't, I'm not, you know, this kind of thing actually, I mean, it's great if you have all the time in the world, you can live in an ivory tower, but the world isn't an ivory tower. At times you have to decide where you're going to draw the line. And the point that I'm trying to make here is that you have to think of, the way that the only thing that saves you from this is you have to be able to put some structure into the way you think and to put some backing into it, to think about what the risks are, and then to go with it and take that risk. Yes?
I think the disagreement they're having is that we just spent however long doing an analysis based on our people cost.
Mm-hmm.
And that Michael's argument really didn't bring that in at all.
Okay, that's a good point. So why don't you ask him about that?
How does that play into your argument?
Well, I would say what we did in the last 10 minutes is totally bogus. But it's very easy for me to very quickly look at what Southwest has done. I have no idea if they're profitable or not, so I'm making that up. But if they are profitable, if I can see that, and I believe they are successful, that's very easy for me to go back to and say, there's this large body, besides the 30 of us talking about something we don't absolutely know.
Okay. So you're basically saying I could easily find that information, and if it turned out to be that it was inconsistent with what I was saying, I could move on to a different thing. Okay, that's a pretty good response. Yes.
Okay, so supporting what Michael said, based on what we've been talking about, we can see here that, based on our charts here, that the proportion of where if you multiply that by the number of airports where you have to do this, you're still going to have a much lower proportion of waste, so your total labor costs are going to be most likely lower. So that, I guess, would support the multi-stop traffic from that one perspective.
Yeah, you could do a little analysis to make that point, to actually bring that point to bear. You would have to do it because someone will question you on those numbers, but that you can do, right? That's an easy thing to do. Yeah. Yes.
For the hub and spoke model, we only analyze the cost at the hub. There's all these spokes that are going to have lots of waste because you're going to have one plane flying in, and you have to staff for that, and then the plane flies out, and then.
Wait, so elaborate.
There's going to be a lot of waste at the spokes.
At the spokes of the hub and spoke system.
Because you have to have all these airports. I mean, your planes are going to fly out and land somewhere, presumably, and then fly back.
Yeah. You had a response to that?
There's just the way I'm thinking of it, but it seems that the multi-stop, you sort of have that same problem too, because there's still going to be airports in the multi-stop where you hardly ever go.
Right.
So I would think of it more as, assuming you have roughly the same number of small stops, but then the hub and spoke, you might have 15 medium-sized ones, as opposed to 2 or 3 big hubs.
If you look at what's going on here, you guys, if you guys are listening to what was going on here about the spokes, right? The key here, the thing that wasn't being, the implicit thing was what is the model that we're going to use for the spokes, right? And so, if you guys are debating, how much it's going to cost, you should first figure out, well, what's the model and what assumptions are we going to make over there? And then you can be on the same page about, why is it this type of what does that graph look like? So, be careful again. Make sure you understand where you all are before you start debating. It's easy to jump into the debate. It's usually hard to sit back and start thinking about, what are we debating about? Okay, but that is a very valid aspect of this. Is your original point, which was, well, there's a hub, but there's also the spokes. We haven't even looked at them yet.
It's not that different in terms of labor costs. I agree. It doesn't seem like, it seems like you save a ton on maintenance and whatever because all your planes go through a given spot and they can take care of what they need to take care of there. But I don't see a labor advantage so much.
Well, once you decide on a model, the thing that you have to decide on is what are the key contributors to the cost there, right? So they might be different in the hub than they are at the spoke. Right, but decide what those are, and then say, I propose that these are the 3, and then once you decide what they are, then it's easy to do an analysis on it. I mean, the way, I'll get to your questions. One thing that I'm getting at here that you see is, it's very good to come up once you're debating. One thing, you can feel really good if you come to a point where you've decided that your decision rests on a set of analyses that you can do, right, in the amount of time that you have, right? That's really, that when you're designing something, that's where you want to be. You don't want to be in a point where you're speculating and, my thing is better than your thing, and that's a disaster. Get to a point where you decide what are the key factors that I need to analyze, what are the analysis that I'm going to do, and then you go do them, and you come back and you've already, in a sense, pre-decided where it's going to go. There's always going to be fuzziness in that, but at least you're getting something done that's going to help you get closer to your answer. There were 2 questions. One was here.
Because we are talking just about the guys who are waiting in the airport for the plane to arrive. We just don't know, or I have no idea if this is one of the main causes This could be the whole analysis. It's not the big thing. If there are 100 guys who make $5 per hour waiting for the
That's right.
an hour.
That's right. And so that's one of the assumptions here, was that the labor was a cost. And I actually read some article about this a similar type of analysis, and labor tends to be a big cost at airports. Yeah, at least you know, at that point, with the economy changing, who knows, maybe.
In this particular case, we did the analysis more at looking at the objective of low cost. And with more analysis, we can figure out which one is low cost. So that's something doable. But once we have done that and say we picked the multi-stop traffic as the low cost one, we have to look at our other objective, which is market share, whether people will be happy flying this. And that's a big risk, I think, in this case, because it might not favor this.
That's right. And that's a very good point. We talked about it a little bit, which was, I thought the most salient comment was this one right here. There's one type of analysis that would help you determine that. I think this one is the one that's most salient, is how much money are you willing to, how much money does it cost to get you to go from a very, two-stop, go to a hub, come back, to one where you have to stop everywhere along the way. And that's some number that you can actually, go out and research.
I think the question of whether your people are flying locally or long distances is also really relevant, because I often find that the hub system is less convenient for the flying that I've done, because you have to fly, and if I want to go to Portland to Seattle, I have to go to Houston and then back to Seattle.
Right, that's right.
I mean, so if they're local flights.
Right, yes.
I mean, just to think of this question along with what you talked about earlier in terms of modularity, probably the best way to have done this would be, okay, we have two objectives, market share and low cost. A few people are going to handle market share, a few people are going to handle low cost. They're going to come up with how they're looking at cost in terms of one aspect is labor, one aspect is infrastructure, kind of come up with the recommendation, then the two groups would meet together, and because they each had a separate module, and then could weigh which one's more important in terms of their...
Welcome to McKinsey. that would work quite well, I think. I mean, it's given what you need to learn here. That's probably how that's probably how I would approach it. There was another question over here. I don't know if I got to it earlier. No? Okay, so I'm going to close up oh wow, we're a little over. So again, the main points here are, it's very likely that you're going to be asked to come up with recommendations and designs where you're not going to know, you're not going to have enough to know the answer, but yet you're going to have to put you're going to have to put a stake in the ground and be able to defend it. That's very hard for some people to do. It's very easy for other people to do. But the real thing you want to get out of it is to learn from it. That should be your objective. Learn from the way others present, learn from others' experiences, from the papers. The thing not to do is, if you show up in recitation and you say, well, I didn't know enough, there's not enough in here for me to make to come up with one side or the other. That's not going to work, because that's not, in the real world, that's no answer, and that's no good. Have fun in recitation. That I posted the assignment for Sunday on the website. If you have any questions, go to the B board or go to the TAs.